Welcome to Math Zone African Motives. Today, we're diving into the fascinating world of logarithmic graphs. By the end of this tutorial, you will be able to define, analyze, and sketch logarithmic functions. Specifically, you'll learn how to interpret the general form of a logarithmic graph and understand its key features like domain and range. We'll also see the special relationship between exponential functions and logarithms by looking at them as inverses. Let's begin by contrasting a function with its inverse, as this forms the foundation for our understanding of logarithms. Our first topic explores the inverse relationship between an exponential function and a logarithmic one. This is a fundamental concept in mathematics. We'll begin with a specific exponential function and then derive its inverse, which will be a logarithm. Consider the function y equals f of x, which is equal to 10 times e to the power of x. This is an exponential function because the variable x is in the exponent. The domain of this function, which are all possible x values, is all real numbers. This means we can raise e to any power. The domain is all real numbers, from negative infinity to positive infinity. The range, or the possible y values, is all positive real numbers. Because e to the power of x is always positive, 10 times e to the power of x is also always positive. So we must be greater than 0. The function never equals 0, and it's never negative. Its output values are strictly positive. Now let's find the inverse function, which we denote as f inverse of x. The key step to finding an inverse is to swap the x and y variables in the original equation. So our equation y equals 10e to the x becomes x equals 10e to the y. This new equation defines the inverse function. Now we need to solve this equation for y to get the inverse function in the standard y equals f inverse of x form. First, we isolate the exponential term by dividing both sides by 10. This gives us e to the y equals x over 10. To solve for y, which is in the exponent, we must use a logarithm. The base of our exponential term is e, so we'll use the natural logarithm, or ln. We take the natural log of both sides. The natural log of e to the y equals the natural log of x over 10. Using the logarithm property that ln of e to the power of y is just y, we arrive at our inverse function. Therefore, y equals the natural log of x over 10, which is our inverse function, f inverse of x. The domain and range of an inverse function are the reverse of the original function. So the domain of the inverse is the range of the original, which is x is greater than 0. And the range of the inverse is the domain of the original, which is all real numbers. This demonstrates how an exponential and a logarithmic function are inverses of each other, swapping their domains and ranges. Now let's delve deeper into the characteristics of logarithmic graphs. Understanding these properties is key to sketching and interpreting them. Let's first define the general form of a logarithmic graph. There are two main types based on the base of the logarithm. The general form is y equals k times log base a of n times x. Here, kn and a are positive constants, and a is the base. The first type is when the base a is greater than 1. Let's look at its graph. Here we see a graph with a base greater than 1. For example, log base 10 of x, or the natural logarithm. Notice it starts down near the negative y-axis, crosses the x-axis, and increases as it moves to the right. The y-axis acts as an asymptote, meaning the graph gets closer and closer to it but never touches it. The second type is when the base a is between 0 and 1. This is a rational number like 1/2 or 1/3. For a base a between 0 and 1, the graph behaves differently. A common example is y equals 4 times log base 1/2 of x. This graph starts up near the positive y-axis, crosses the x-axis, and decreases as it moves to the right. Again, the y-axis is the vertical asymptote. Regardless of the base, all logarithmic graphs share several key characteristics. First, the graph represents a function. This means for every x value in the domain, there is exactly one y value. It is also a continuous graph, meaning there are no breaks or holes. Second, the graph is not symmetrical about either the x-axis or the y-axis. Third, and very important, the domain for the basic form of the logarithmic graph is all positive real numbers. This is because you cannot take the logarithm of a non-positive number. However, the range is all real numbers. This means the y values can go from negative infinity to positive infinity. Finally, as we saw earlier, every logarithmic function has an inverse function, which is an exponential function. To recap, we've seen the two forms of logarithmic graphs and outlined their fundamental features. Now we can apply this knowledge to sketching them. Let's move on to sketching logarithmic graphs. We will work through example 4.13, which asks us to sketch three different logarithmic functions on separate axes. Remember our key features: the vertical asymptote at x of 0, the domain psi x issue, and the general shape that depends on the base. The base a tells us if the graph is increasing, a1, or decreasing. A very useful point to plot is the x-intercept, where y equals 0, 0. We'll set the argument of the logarithm, the part inside the parentheses, equal to 1 to find this point. Let's start with the first function. Number 1, y equals 2 times log base 10 of 3x. First, the base is 10, which is greater than 1, so we know this graph will be an increasing function, going up from left to right. Next, let's find the x-intercept by setting the argument equal to 1. We set 3x equals 1 and solve for x. Dividing by 3 gives us x equals 1/3. This means the graph crosses the x-axis at the point 1/3, 0. Now we can sketch the graph. Draw a coordinate plane. Draw a vertical asymptote at the y-axis, x equals 0. Plot the intercept at 1/3, 0. Then draw a smooth, increasing curve that approaches the y-axis but never touches it, passes through our intercept, and continues upward to the right. And that's the sketch for our first function. Now for the second function. Number 2, y equals 4 times the natural log of x. Remember, ln stands for log base e. The base here is e, which is approximately 2.718. Since e is greater than 1, this graph will also be an increasing function. Let's find the x-intercept. We set the argument x equal to 1. This is a special property of natural log. So the graph crosses the x-axis at the point 1, 0. Again, sketch the coordinate plane and the asymptote at x equals 0. Plot the intercept at 1, 0. Draw a smooth, increasing curve that approaches the y-axis, goes through the point 1000, and continues upward to the right. Great, let's move to the final function in this example. Number 3, y equals 3 times log base 1/4 of x. Here, the base is 1/4. Since 1/4 is a number between 0 and 1, this graph will be a decreasing function. Let's find its x-intercept. Setting the argument x equal to 1, we find the intercept is at 1, 0. The intercept is at 1, 0, just like the previous graph. Now sketch the graph. Draw the coordinate plane and the vertical asymptote at x equals 0. Plot the intercept at 1, 0. Draw a smooth, decreasing curve that approaches the y-axis, passes through 1, 0, and continues downward to the right. And there you have it. You've now seen how to sketch logarithmic graphs by identifying their key features based on the base of the logarithm. This completes example 4.13. We'll now move on to our final example, example 4.14, which brings together what we've learned about inverse functions and graphing. We'll sketch an exponential function and its logarithmic inverse on the very same set of axes. This example emphasizes the key principle that the graphs of inverse functions are reflections of each other over the line y equals x. The question asks us to sketch the graph of y equals 10 times e to the x and its inverse on the same axes. We also need to state the domain and range for both graphs. We've already done most of the analytical work. We found the inverse function in our very first scene. So let's list our given information. Here's our given function, its domain and its range. And here is its inverse function, the natural log of x over 10, along with its domain and range. Having these features identified will help us draw the graphs correctly. Let's first sketch the original exponential function. For the function f of x equals 10e to the x, let's find the y-intercept. We do this by plugging in x equals 0. Since e to the 0 is 1, our y-intercept is 10. The graph passes through the point 0, 10. Since the base e is greater than 1 and the coefficient k is positive, the graph is an increasing curve that approaches the negative x-axis but never touches it. The negative x-axis is a horizontal asymptote. Now for the inverse function. For the inverse f inverse of x equals the natural log of x over 10, we'll find the x-intercept by plugging in y equals 0. To solve this, we need to remember the definition of a logarithm. For the natural log, that means e to the power of the right side equals the inside. So e to the 0 equals x over 10. Since e to the power of 0 is 1, we get 1 equals x over 10. Multiplying both sides by 10 gives us x equals 10. So the x-intercept for the inverse is 10. The graph passes through the point 10, 0. Let's put it all together. First, draw the dashed reflection line y equals x. Then sketch the exponential graph passing through 0, 10 with the negative x-axis as its asymptote. Next, sketch the logarithmic graph passing through 10, 0 with the y-axis as its asymptote. Notice how the graphs are perfect reflections across the dashed line. For instance, the y-intercept, 0, 10, of the original function reflects to become the x-intercept, 10 thashes of the inverse. Finally, we state the domains and ranges, which we already determined. Here they are again for clarity. The domain of one is the range of the other, and vice versa. This confirms our analysis. Let's quickly recap what we've accomplished in this tutorial. First, we explored the concept of inverse functions, demonstrating how exponential and logarithmic functions are opposites of each other. We saw that they swap their domains and ranges. Next, we detailed the general form of a logarithmic graph. We learned that the base a determines its shape and direction, with a base greater than 1 resulting in an increasing graph, and a base between 0 and 1 producing a decreasing graph. We also identified the key features common to all basic logarithmic graphs. They are continuous, have a domain of x greater than 0, a range of all real numbers, and a vertical asymptote at x equals 0. Finally, we put this theory into practice by sketching several logarithmic graphs and an exponential graph with its inverse. We confirmed that they are reflections over the line y equals x. You should now be able to interpret, analyze, and sketch basic logarithmic graphs and understand their relationship with exponential functions. Thank you for watching. For more detailed tutorials like this, remember to subscribe to Math Zone African Motives. See you next time.